This is problem 7-68. It's on page 361. Draw the shear moment diagrams for the simply supported beam. This beam is interesting. I selected it because it has a point load and a point moment load. So it looks something like this, at least in skeleton format. Point A is pivoted, point B is a roller, so it's a simply supported beam. There's a concentrated moment of 2 kilonewton meters located 2 meters from end A. And then there is a concentrated load of 4 kilonewtons at 2 meters beyond that point, and then a further 2 meters to the end of the beam. So it's all set up nicely. If we make a free body diagram of this beam, obviously we've got the 2 externally applied loads, one being a moment, the other being a point load. But then there are also reactions at A and B. So if we sum moments about point A, taking counterclockwise as positive, well, let's see. The first load we encounter is this moment, and that moment is a negative moment. And then we've got the moment of the 4 kilonewton load, which is also a negative moment, so 4 kilonewtons multiplied by a distance of 4 meters. And then the moment of reaction B, which has a 6 meter moment arm. That all sums to 0. So if we rearrange and solve for the reaction at B, it turns out to be 3 kilonewtons. So 3,000 newtons is the reaction at B. If we sum forces in the y direction, then we'd have A plus B minus 4 kilonewtons equals 0. Notice the moment does not appear, and it may seem odd that it doesn't, but in a way, it's hidden in the reaction at B. So rearranging this, since we know B, to solve for A, well, A is 4 kilonewtons minus whatever B takes up. Well, B takes up 3 kilonewtons, so apparently A, the reaction at A, is a kilonewton. And of course, the reaction at B, as we've already discovered, is 3 kilonewtons. Notice that the moment load at M doesn't change the sum of reactions A and B. Rather, what it does is it changes the distribution of the loads A and B. Now we know that the shear diagram can be easily drawn just by considering the loads and the reactions. And if you imagine a beam that's cut here, well, if we've got a kilonewton here, we better have a kilonewton of shear there. So 1 kilonewton is where we begin. And you notice that there are no loads that can cause a change in the shear, because a moment can't do that, until we reach this 4 kilonewton load. Now what this load does is it moves us down by 4 kilonewtons. So this overall height is 4 kilonewtons. We end up at negative 3 kilonewtons here. Now a way to think about that is, what if we cut the beam at this point? Well, then we got 1 kilonewton up, 4 down. Our shear had better push up with 3 kilonewtons, right? And the only way to do that is if it's not pointed downward, if it's pointed upward, which is a negative shear in our convention. Now we go over here, and not surprisingly, we end up with a reaction load of 3 kilonewtons, which brings us back to 0, because we're out of beam material, right? So we better not have any shear by the time we leave the beam. Now the moment, as we learned, is simply the integral of the shear. So as we move along the length of the beam, of course it's in meters, we start at point A with no moment, because there's no way that a pin can provide a moment to the end. And all we really need to do is calculate area. Now I'm going to go ahead and just calculate area to this point. It's pretty easy. This area is just a rectangle, so it's a length 2 meters times a height of 1 kilonewton. Simple. So 2 kilonewton meters. So we end up at 2 kilonewton meters. I'm going to need more space. I better move that down just a bit. So we end up with 2 kilonewton meters at this point, and a linear increase because the area increases linearly. If you think about cutting the beam here or here or here, the amount of area is just proportional to the length of the cut, right? From A over to the cut. So this is just a linear line that goes up and lands on 2 kilonewton meters. Now at this point, there is a 2 kilonewton meter load that's also trying to torque the beam to the right. So our clockwise. So our internal moment has to overcome that, as well as the moment of the shear and the reaction load. So there's a further 2 kilonewton meter increase in the moment within the beam, because if you make a free body diagram and say cut the beam here, there had better be even more moment to counteract that externally applied moment. Okay. Now, as we move along farther and farther, what happens? Well, more and more area accumulates. In other words, we're going to need more and more internal moment in order to resist motion within the beam. As a matter of fact, this area is also 2 kilonewton meters worth of area, and so we go up a further 2 kilonewton meters. Then finally, negative area causes a decrease in the moment, and so we've got -3 times 2, this area is -6 kilonewton meters. And so we go down, well, not surprisingly, we're at 6, we're going to go down by 6, so we end up at 0. No moment or cantilever at the end of the beam, so we end up at 0 with a linear decrease. As a matter of fact, what you'll notice is that the slope of this line is -3 to 1, right there. It's the magnitude of the shear. Just like the slope of this line is simply 1 kilonewton per meter? No, 1 kilonewton meter per meter. Got 1. Same thing as this, the slope here is also 1. Because the shear diagram tells us the slope. So if you want to know the slope of the moment at any point, just look at the magnitude of the shear at that point and you'll know the slope. So that's it. We've made a shear and moment diagram indicating the magnitude of the shear and the moment within the beam. If we were to cut the beam at an infinite number of places, this is what we would find for the shear and the moment.